Hi everyone, and welcome to sections 3.9 and 4.1. So these two sections are fairly different, but they're both just applying these derivative ideas to the derivative function to something in order to get something. So it's just kind of like applications, so we're squishing them together. So we're going to do this video in pieces. The first thing we're going to do is section 3.9, which is linear approximation and differentials, and then we'll talk about 4.1. So let's just jump into it. So section 3.9 is about linear approximations and differentials. This has got a big fancy name, but it's nothing more than us just kind of rewording the tangent line and using it differently than we have. But that's it. If you see linear approximation differentials, you're really just kind of thinking of the tangent line with that. And so when you see something that says find the linear approximation, linearize something, anything like that, you're just finding a tangent line, which we all know how to do. So, immediately just you've got all of this knowledge that you've gained that pretty much takes care of almost all this. We're just going to see why we do it, talk a little bit about it, see some examples, just to kind of see a different way of thinking of the tangent line. So here's the whole point, and it's all based on this picture here. If I give you a function f and then a point a, so far what we know is that we can create this tangent line at a, right, by saying, okay, well, the tangent line, I know that the slope m is just take the derivative and plug it in, right? So, okay, I can get the slope of this line, and then I know a point on the line, whatever this number is, and then plug that into f. So I know a point, I know a slope, so I can draw this tangent line. And so the goal of this is to say, okay, well, at this point, right here, these two things agree, right? F of x and then what we are calling L of x, the tangent line, we're calling it L of x because, we're pretending like it's a new thing and we're trying to be all fancy. But it's really just the tangent line. So these two things agree at this point. And what we see when we draw tangent lines is that actually, it's not just A here, right? Let's go out a little bit further here and here. If we zoom in to this, really it's difficult at all to tell the difference. Here, I'll zoom in. So I'll zoom in here, and if we zoom in, it's very, very difficult to tell the difference between the blue and red lines here. And so what that tells you then is that the function, the blue function, and this tangent line will have very similar y values for any number in this little range here that I plug in. And so why is that useful? Well, if the function itself is very complicated, it might be hard to use. It might be hard for a computer to use. It might be hard for you to use. And by use, I mean plug in numbers to evaluate. Well, so if that's true, this purple one, this red purple, is just a line, like just a line. Y equals mx plus b. It's pretty easy to plug numbers into a line, right? So if I'm over here in this little range, I would much prefer to use this line, y equals mx plus b, to plug numbers in than a possibly complicated big equation for this function f. So we are linearizing this function f, which might be really crazy looking. We're saying, okay, that's too much to deal with. I can make a straight line that mimics that function in this little area. And if I do that, then as long as I'm okay with a little bit of error, I can do things like say, well, maybe this little b here, I can say, I can find an approximation. F of b is going to be approximately, this symbolizes approximately, my tangent line plugged in at B. It's not going to be perfect, but it's going to be pretty close. So these, in case you haven't seen this before, double squiggles means approximate. We're approximating. So that's the idea. We're zoomed in close enough here, hard to tell the difference between the two lines, so why don't you just use the one that's y equals mx plus b instead of this possibly crazy looking f of x. Of course, then, you get too far away from this starting point of a, and they start to break apart. And so, this idea works when you're close to the value that you've started with. And that's the idea. That's linearization in a nutshell. F of x, gross, get it out of here. Just do the tangent line and use that as long as you're close to the original point you started with. Boom. That's it. Done. So if you're interested in this more, you see a lot of really cool ways this is used. This is used by computers to evaluate things approximately because a computer likes a straight line, y equals mx plus b, more than some other complicated equation that it might try to plug into. This is useful in physics when you have equations. One that you can look up is a simple pendulum. That equation relies on an angle, and in the differential equation, which you can go look up, basically the equation that talks about the pendulum, there's a sine theta. Ugh, terrible. But, and here's, if you're really interested in that, what you can do, just kind of off to the side here, is, and I show this, sine theta is approximately just theta, right, for a equals 0. So if you take the function sine theta, sine x if you don't want to deal with thetas, that's okay, sine x, and you say make the tangent line at a equals 0, then the tangent line you're going to get here is just the line y equals x, and it will be really close to the value of sine for any input near 0. And so what you can do then is, in this kind of gross pendulum equation, you can substitute, take away the sine and just put theta, because as long as your angle is then close to 0, it's not a big deal. It's going to be okay. You're not going to be perfect, but it's going to be close, and that equation becomes better to solve. So that's just one other kind of little tidbit of why this idea might be useful, because it can again, it can just simplify equations as long as you don't need to be perfect. So something you can go check out the pendulum. Okay, so that's linearization. That's the idea of it. And so when we want to do linearization, all we have to do is find the tangent line. That's it. You got this big L, we call it linearization. Oh, we're so fancy. No, it's just the tangent line. Just go find the tangent line. That's it. So we're going to do some examples to kind of show this off. Okay. So we're going to skip differentials for just a second so we can get to these. So number 10 says, find the linear approximation of this function at a equals 0 and use it to approximate these numbers. All right, so here we go. Linear approximation. Remember, just do the tangent line. That's all this is telling me. Tangent line. Okay, so I know how to do that. I need to take the derivative, right? So then, just to rewrite this to make this better on ourselves, this is to the 1/3 power. Drop it. 1 plus x, right? Subtract. Times the derivative of the inside, which is just 1, so okay, we're good there. A equals 0. That goes inside. So then that gives me g prime of 0 is 1/3, 1 plus 0 to the negative 2/3. 1 to this power is just 1, so that gives me 1/3. Okay, so then that's the slope of my tangent line. So my tangent line itself then, my linearization, to use our fancy terminology, is going to be, well, 1/3 x minus 0 was the point I had started at, right? And then it's going to be plus, and then we actually just need the y value here, right? So this is going to be g of 0. So it's just like making the tangent line we're used to. So then g of 0 is cube root 1 plus 0, which is 1. So then altogether, my linearization is 1/3 x, 0 makes this 0, plus 1. Okay. All right, so good. That's a good start for this. Now, why are we doing this? What's one reason? Well, what if I wanted to know what the cube root of 0.95 is? Right? I want to know what this is. Well, this is pretty hard for us to try to do. We don't really know how to do cube roots of numbers that aren't really nice numbers, right? Like 8. Cube root of 8 is 2. Woohoo. But 0.95, I don't know. What number, times itself is 0.95? So how would we do this? We have 0.95 under the cube root. Well, the first thing you have to do is connect it to your function. Our function, our original one, was this, right? So in order to get 0.95 in there, x has to be negative 0.05. Okay, so we really want to know what this is. That's the same thing as plugging x equals negative 0.05 into this function. Okay, so negative 0.05, right? That would be about right here. Negative 0.05. That's the x. And then all you gotta do is just go up here and look at how close the linearization, that's in yellow here, is to the cube root of 1 plus x function, which is in blue. Look how close they are together. If you zoom in even further, which is right over here, you see that, right here, there's definitely a difference between them, but it's a very tiny difference here. Very, very tiny. You can see that from these numbers here. Okay, so then how do we find the linearization to do this? Well, x has to be this number so that these are the same thing. So all you do is take that x and plug it in for your linearization. That's going to be L of negative 0.05, which is 1/3 times negative 0.05 plus 1. And that's it. We don't have to do a cube root, right? No cube root here. All we have to do is plug into this linear equation. So there you go. That's all you got to do. Now we should actually find out what this is, right? So we can open up our calculators. We do 1/3 times, so we got 1/3 times negative 0.05 plus 1 ends up giving me, so this equals 0.983 repeated. So that's what the linearization tells me. Okay. Now, what you should do then is you should also plug in, right? You should plug into your calculator cube root of 0.95. See what happens. So we can do that. 0.95. That's going to go under a cube root. That gives me 0.9830, and we'll round there. So this is rounded. Look how close those are. Tenths digit, same. Hundredths, same. Thousandths, same. It's not until you get 4 digits in that they're different. So I like using the line better than trying to figure out what's going on with a cube root. So there you go. So that's how we could do that for 0.95. Now for 1.1, what we'd have to do is, again, you got to compare. I want cube root of 1.1. Well, again, compare that to your original function. And then you got to think, how do I get these two to be the same? Well, x has to be 0.1. So if I want to approximate this, cube root 1.1, I want to approximate this, I just have to plug that into my equation, my linearization equation. 0.1 plus 1, right? So that's going to equal, just plug it in, 1/3 times 0.1 plus 1. That's going to equal 1.0, and then 3 repeating. And then we can actually do this in our calculator. Right, we're going to have to round again, but still. 1.1, and then we're going to put that inside the cube root. And we end up getting 1.03228 ... Look at that. These differ at the third decimal place. Now, stop and think about this for a second. This is something that you could, it would be pretty easy to just kind of blaze past this. This was all the way good till 4 decimal places. This one only till 3 decimal places. Was this accurate? Why? Well, think about this. For this one, I went a full 0.1 away, right? I'm a full 0.1 away from a equals 0. This one, I'm only 0.05 away. It's negative, but that's not the point of this. It's the absolute value. How far away did I go? So technically, this one is double the distance away from my original point where they perfectly line up than this one is. So the further away I am, the worse my approximation is going to get. All right? So little things to think about when you're going through this. But there you go. That is how we can do this approximation. So there's an approximated value for 1.1. There's an approximated one. And we got it. Okay. So the next piece of this is called differentials. And again, we're going to go back up to where that's defined. It's not anything like super crazy new. Basically, it's the same ideas behind these linear approximations. It's just notation that is going to actually be very beneficial for us later, especially in Calc 2. So in Calc 2, this notation's really, really nice to be able to use. And so the idea behind this is we can talk about functions and their change using the same tangent line idea. And we talk about that using this equation. These are the differentials, dy and dx. These are differentials, okay? And it's very similar to what you may have seen before with delta y, delta x. These are similar things. They're all kind of connected. And it's just trying to tell you change. So what does this equation say? Let's zoom in a little bit on it. What does this equation say? It's basically saying the change in y for your function is equal to, well, what's your derivative there? Because what is derivative? Derivative is supposed to be change. So, okay, the change vertically you're going to get is your derivative times the change in your horizontal. So you're sitting on a function, right? This is the picture. And there's one below that's much better than this one, but we're going to do this one anyway. You're sitting here on a function. Like, okay, where do I go now? Well, how do I figure it out? I'm at some x value. I'm going to move, right? I'm going to start moving to the right. I want to start moving to the right. And I'm going to talk about that move using dx. Dx is going to represent this movement to the right. Okay? Now, how do I figure out where to go to stay on this function? The idea behind linear approximation, behind these differentials, all of that stuff is, well, all you got to do, right, find the derivative at this point, right, which remember, slope of the tangent line, okay? And then the idea is, well, you could get really close to where you should go by just going follow the slope. So how do I follow this slope? What do you mean by that? Well, what we mean by that is this slope, m, is supposed to tell you how to change vertically given a horizontal change, right? That's what slope is, rise over run. So following the slope is the same thing, which I'll just write here. Following the slope is the same thing as taking that slope and multiplying by your dx, your step. So I'm gonna, I got my slope. Okay, I'm gonna go that direction. It's a direction. Now, how far do I go? Well, I'm gonna just start moving horizontally. That's dx. And the bigger dx is, the further you're going to follow this slope. If dx is really small, you only follow it just a little bit. If dx was really big, you would follow this slope for a long time. But what did we just see? If you follow the linearization for too long, you may get very far away from the function. But this is it. It's just different notation. Dx, again, is saying change horizontally. How big of a step do you want to take to the right? Dy is saying, okay, well, how you did that. How far did you change up and down? And those are related by the slope. Right? Just rearrange this for yourself. Dy dx equals f prime. Right? Change in y over change in x is the derivative. So we're just developing this notation to rewrite that idea in a slightly separate way, but it's same idea. So there's a fancy picture down here. We can go look at this fancy picture relating all of these symbols you may have, remember seeing before. So this picture can be a little bit much, but the idea here is dx, and it's mentioned above, is an independent variable. So you control this. This is something that it's like a little lever you can turn. A lever? No, it's like a little, like a knob. You can turn dx. You can make dx really big, you can make it small, whatever you want. It's just how far to the right are you going to step. So okay, I can choose how to go as far as I want here, but they gave us in this picture a dx, a step to the right. Now, delta y is the honest to goodness actual change of the function. This is the real change in y. Okay? And what we're saying here, though, is dy, which is the change in y following the tangent line or the linearization, right? L of x, if you want to use the linearization, if you want to think the tangent line, however you want to think of this. Dy is how did you change if I was going to follow that the entire time? Okay, so that's it. That's all these notations are saying. And so what they're saying is dy is given by this formula. Follow the slope some amount. So take a step to the right, follow the slope that way. And the idea is if you take a small enough step, right, then dy should be pretty similar to the real honest-to-goodness change in the function right here. So this, if you stay close enough, should be pretty close to that, which we've already seen. Right? It's just this is a certain language to use to talk about it. That again, it's connected to all this. This is why we bring it up now. It's really useful in later ideas to have this notation in our back pocket to use. So, that's it. And we'll do an example or two to see like how we use it, but it's not anything new. So let's go down here. Let's check out the example. Okay, so it says, let y equal square root x. Find the differential. So dy is, take the derivative, dx. All the time, every time, this is the formula. So we need to take the derivative here. So if this, we're just calling this f of x to fit this notation. This is equal to x to the 1/2. What's the derivative of that? Well, f prime is going to be 1/2 x to the negative 1/2. Okay. So then you just plug it into this. The differential is 1/2 x to the negative 1/2 dx. So what's this say? This says if you want to know how y changes, right, given a small change in x that you pick, right, this is a small change in x that you're going to pick, then all you got to do is plug into this formula. That's it. You plug in your x value that you're starting at. You plug in what you want, how you want to move in x, how far you want to move, and that I'll tell you about, as long as this is small, about how the real change in y will be. But again, this is not the real change in y. This is just how far up did I go or down following the tangent line. So that's something you gotta get in, just as a reminder over here, right? Delta y is the real change in f in your function, right? Dy is the change following the tangent line, which we saw a bunch of times is not going to be perfect. But if you're close to your original point that you started defining the tangent line at, then you're going to be close enough. So okay, so it says evaluate dy and the real change in y if x equals 1 and we take a full step of 1. So dy is 1/2 1. It's just as simple as plugging these things in. Do not overthink. Dx is 1. So this is 1/2. So let's just stop. What did I just say? Well, if I start at x equals 1, and I'm sitting on this curve at x equals 1, if I just follow the tangent line here, a full step to the right, follow the tangent line, I will go up by 1/2. That's what this says. I'll say it again. If I'm sitting on this curve at x equals 1, and I decide, let's follow the tangent line for one full unit step, I will have gone up by 1/2 unit. On the other hand, if I decide to follow the function and not the tangent line, right, how's it going to change? Well, this one's not too bad. I want to know how the function changes between 1 and then take a step to the right, aka 2. Okay, well, just, plug in the function. Plug in 2, plug in 1. Tell me how far you went. Right? Where am I when x equals 1? Just plug it in. Where am I going to be when x equals 2? A full one step to the right? I don't know. Plug it in. So we just go into our calculator and we type square root of 2 minus 1. Square root of 1 is 1. And we get 0.414 some extras. Remember, this is 0.5. So look at that. It's not terribly far off. It's not good, though. We're already in error in the first decimal place, in the tenths place. But you got to remember, we took a full step to the right. That's a pretty big step to take. And we're not crazy far off from this. But that's it. That's it. This is literally it. This is it. This is it. This is it. This idea of a differential is a way for us to kind of still talk about this linearization idea. Just kind of give us a different set of words to use to describe it. Okay. So, C says, sketch a diagram like figure 6 showing the line segments with these lengths. So, are you ready to completely butcher this? Here goes nothing. So, we have y equals square root x. Okay. So, we are interested in 1 and 2, right? 1 and 2. So that's going to be 1, and this will be 2 over here. Okay, we also know 1 and then 2. Boom. So my function square root of x, 0, 0, hits there. So we'll draw this in this color. So I'm here, and then at 2, I'm only 1.41 something, so we'll call that like right here. And then we're going to try to connect these. Wowzer. That was next level. Okay, great. Don't start sending me pictures of your perfect curve because I know you did it more than one time and you erased. Don't mess with me. So that's square root x. Okay. Now, we just are trying to draw these ideas so that we can show we have them in our head. Now, we started at 1, right? So then what did we do? We took a step, dx was 1. That's our step. So we do. This was our step, dx. A full one step to the right here. Okay. Now, check. What was dy? So, here's the thing. dy is the change if you were to follow what? Follow the tangent line. Okay? So we are going to go next level here, right? And we're going to draw in this tangent line, and we're not going to mess around. Boom. Tangent line. Okay. So we've got our tangent line, and we're going to make it, can we make this a little bit weightier? Yes, we can. So that's our tangent line. Okay. So then dy, right? What's dy? dy is the change in y if we had followed the tangent line the whole time. Okay, so what did we say? dy was going to be what? We calculated this, right? 1/2 or 0.5, however you want to look at it. That's going to be the change from 1 up to 1.5. So here's 1.5, and we're just going to, yep, perfect. Look, my tangent line's perfect. Everything's perfect. Don't even worry about this. So this change here, this change, that's dy, that change from top to bottom. So from 1, I went up to 1.5. And again, we're going to pretend that this is 2, 1.5. Okay, so that's dy. That's how much I changed if I followed the tangent line. So what's delta y? What's delta y going to be? Delta y, that's the honest to goodness actual change, right? Which we figured out was 0.414 and some change. That's the actual change here to here, right? This is delta y. That's the actual change. So this full change is our using the approximation. That's what we think should happen. This is really what happened if I take this full step. So even from the picture, it's hopefully not too bad to see that, yeah, this is going to be an overestimate, right? And one thing you could think about, you could talk about is like, can we talk about this function, properties of this function, to know if we're going to do an over or under estimate? And you can. We're not going to go too deep into that, but it's something worth thinking over. So there you go. There's our little diagram. Okay. So we got a new problem here. It says the radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. So this is interesting. The idea of problems like this is when we are doing measurements, we often have error because we can't measure anything perfectly. And so these ideas of differentials give us a way to explain what the maximum error could look like if we measure one thing and try to use that to relate to another. Okay, so we are interested in using differentials to estimate the maximum error in trying to calculate the area of the disk. So, first things first, right? Area of a disk is what? Pi r squared. Okay. So what's this telling me? What we're trying to understand here is I'm going to have to give you a radius to find the area. That's what the equation says. So that hopefully that's not anything too crazy. But I can't give you a perfect number here. There is a possibility of error in this radius. So the question we're trying to really get at is what happens, right? What happens to that error if I put it into this function? Right? How can the error grow if I calculate area now with this radius that might not be exactly right? Okay, so the point of this is if there's a 0.2 centimeter error in my radius calculation, then that error is not going to be the same as the error I should expect, or the maximum error I can theoretically say there will be in the area. It's going to be different, and differentials helps us do that. Okay, so we've got area equals pi r squared. Now, just, you might be thinking like, what? Like how does this relate to differentials? You know, let's just try, just apply differentials here, right? Remember, dy equals the derivative of our function, right? And in this case, we should be a little bit careful. We should use the notation that we're using, right? dA is going to equal the derivative of this function, which we can call f, times dr. Now, dr, this represents the error, maximum error that we're discussing. And so you got to think about this, right? It's that small change we're making in R. We're saying, yeah, there could be a small change in R. And the goal is to say, like, okay, well, if there's a small change in R, what will that look like in A? That's what these differentials allow us to do. The small change in R, what's going to happen? And it should somehow relate to this function here, right? And that's where this comes in. So let's just do this out. dA equals, take this derivative, 2 pi r dr, okay? So we have our radius measurement, 24 centimeters. So the maximum error in A is 2 pi, the radius that we have, times, and then what's our maximum error here? 0.2 centimeters. Okay, so then we can get out our calculator, and we'll write this a couple different ways. So 2 times 24 times 0.2. So this is equal to 9.6 pi centimeters squared. Don't mess around with these units, you gotta pay attention. And then we'll just multiply by pi to get an idea. That's about 30.16 centimeters squared. Okay, so what are we saying? And this might seem like a crazy number to you, but this is why this is so useful, because maybe your intuition is not thinking this. With only, and maybe I shouldn't say only here, this is a decent size error, with a 0.2 error, possible maximum error, because of what we're using to measure things, maybe our ruler, is broken up into 0.2 ticks, and so we don't have anything more exact to use to measure the radius. That's for physics class. You can go ask your physics professor. So if this is our maximum error in the radius calculation, that could become an error as large as 30 centimeters squared in the area calculation. Big. So it's useful to know. This is important. It's a useful idea to know whenever you're measuring something. And differentials allow us to do that. And the only connection you have to make here is that dr and dA are going to represent how, this change that could happen because of the error. Okay, so hopefully not too bad. So what's the relative error and what's the percentage error? So relative error, we have that. Percentage error, right? So the percentage error is just, 30.16 centimeters squared over, and then we have to take the actual area itself to divide this to see how big that is compared to the actual area. So the area itself would be pi r squared centimeters squared. So we're going to do some division here. And actually, if you want to be more exact, we should use this 9.6 pi centimeters squared, right? So if we're really trying to be more exact, we could even be more exact than that, we could alternatively use the 9.6 pi centimeters squared, because the same thing, over pi times 24 centimeters squared. And if we do it that way, the pi's cancel, which is nice. Not necessary. You could just do things in your calculator, not worrying about it, but it is nicer. 9.6 divided by 24 squared is going to give me 0.016 repeating, right? As a percentage, that's equal to, as a percent, 1.6 repeating percent error. Okay? And so what you should be thinking about from this is go back up here, because that number might be like, so what? This was percentage error, right? Calculate this, because this as percentage error was 0.2 divided by 24 is 0.0083 repeating, which is 0. And then 1.283 repeating percent. So this was less than a percent maximum error, but going through the area calculation jump that up to over 1.6%. So we got to be thinking about that here, okay? That's something to really think about.